Hello, calculus students, and welcome to another online lesson. We're continuing our unit on integrals, and today we will be talking about how to utilize integrals to find volume, specifically by rotating our functions around the x-axis. Hopefully, it should be a pretty interesting one. So to start with, we are going to give you a formula for volume of revolution, it's called. So if we think of having a specific point here on any curve, if we take that point and we sort of rotate it around the x-axis, where the radius is going to always be the height or the y value involved there. You think of that y value, which is known as our f of x, and we do pi, which is a coefficient, and this y value, which is like a radius here, and we square it, pi r squared. That's all it is. But then through calculus, we essentially have all of these, infinite number of circles that are being created, like we did with area. We're rotating all of those, and that ends up being volume. So it's really just based on this old concept, but once we involve calculus, it allows us to do these volume problems. So in the diagrams here, you can see that this original function on the left, f of x, turns into, whoops, turns into this sort of cylinder type shape, or it's got cone aspect, but it's parabolic basically, or exponential or something like that, and again been rotated around to make this very interesting shape. It still has boundaries or borders at A and B. We're still going to utilize our fundamental theorem of calculus and all the other properties we've learned, but that's where we start off. Now we can also utilize this idea of having two functions or an area between two curves and rotate those as well. And we do the same thing that we did before, but we square each of the functions individually. You don't have to square the outside and utilize some sort of FOIL or anything like that. That is not needed. We just square each function that we're being subtracted. And it's the idea of, if you do one function and you find its volume, and then you do this bigger one, then you can sort of create this washer shape by subtracting this intersection out. And that's what's happening here when we subtract our second function. So what's new? The only thing that's really new is we put a pi on and we square our functions. We've done area between curves, and that's what we see here on the second formula. And we've also done area beneath a curve. We're just now rotating it to find volume. So let's take a look at one example, and we'll save the second example for in class. So find the volume of revolution generated by revolving the region between y equals x squared and y equals the square root of x about the x-axis. So those are essentially inverse functions. And we want to find out where they intersect. It's already been shown to us here on this particular diagram. And we could also check that by simply setting the two equations equal to each other to find out where they intersect would be another way to solve this. But either way, we get an input of 1 as our upper boundary, and we have 0 here as our lower boundary. To set this up, we are going to do pi times the integral of 0 to 1 of our two functions. Now the one that's on top is actually the square root of x, or x to the 1/2 power, minus x squared. Now each of these functions I'm going to, and that's all going to be dx here. Each of these functions now need to be squared, and so I can go back in here and square this one, go back in here and square that one, and that would be my setup to this function overall. Now we're going to do our integral, but as we simplify things here, it makes the math a little bit easier. So I have just x minus x to the fourth dx. And then if I want to, I can break these up into two separate integrals, or I can just do the integral all at once. And I think I'm just going to do it all at once here. So again, my constant of pi is out front. I'm going to need to use parentheses now because I want to show that that pi is still out front. Or here's maybe even a better way to do it. I could take the pi and put it on the other side of my bar. So I'm going to move the pi over here. And the integral of x, well, I raise the exponent up to a 2, and then I multiply by 1/2. And here, I'm going to raise the exponent up to a 5, and then multiply 1/5. And that's all still going to go from 0 to 1. So as I plug in my 1, I'm going to have 1/2 times 1 squared minus 1/5 times 1 to the 5th minus 1/2 times 0 squared minus 1/5 times 0 to the 5th power. And then all of this is going to get multiplied by pi. So all of my zeros over here on the right essentially cancel out. And on the left here, I just end up with 1/2 minus 1/5, all times pi. Common denominator here would be 10, so I have 5/10 minus 2/10, all times pi. And that ends up being 3/10, so 3/10 pi, or 3 pi over 10. That's units cubed. And that would be my volume. Again, we'll look at another example in class next time, and there's a few problems on page 491, numbers 1 through 3 and 5 that you can take a look at between now and then. Till next time.